Hello everyone, my name is Max Trigup and this is my Physics Lab 2 where I examine the relationship between vertical position and horizontal position, time, force, and acceleration. For this lab, I performed this lab to observe how velocity, force, and vertical and horizontal position are interrelated. And to find this out, I utilized Newton's second law of motion, which is sigma F equals ma, or the sum of all forces is equal to mass times acceleration, and the definitions of position, velocity, and force in my lab. In this lab, I also discovered that during projectile motion, the relationship between vertical position, vertical velocity, and time is quadratic, meaning that as an object moves along a path with two dimensions, time is square. Also, drag force decreases velocity, and there's no terminal velocity at short distances, such as the one showed in this experiment. I assumed that the ball's horizontal speed was always constant, because with little to no air resistance, horizontal speed is constant. The initial velocity could be accurately calculated based on the initial position and time values. The meter stick appears as 1 meter long in my recorded video, which of course is not true due to camera lens effects, but I assume that it was true, and that the drag force could be accurately modeled by the given equation F drag equals negative BV squared. For my procedure, I threw a crumpled paper ball approximately 1 yard at a constant speed. I tracked the paper ball's position over every frame of the video I recorded in the tracker program. I compiled the position values into a spreadsheet. I then recreated my experiment in GlowScript and exported those position values into the same spreadsheet, with those position values being both with drag present and without drag present. And then I graphed both sets of values, meaning my tracker values, both pairs of tracker values, and my real experimental values, and I compared them. This is the video of my lab partner throwing the crumpled paper ball. As you can see, it traveled around 1 meter horizontally and 0.75 meters vertically, and it followed general projectile motion principles, with those being that its acceleration could be modeled by the constant g, and it had a constant velocity to the right in the horizontal direction and a changing velocity based on g in the vertical direction. This is my GlowScript code as well as my final animation in GlowScript. The green line represents the path of the crumpled paper ball. The orange arrow represents the unit vector for the force of drag on the crumpled paper ball. The blue arrow represents the acceleration due to gravity on the crumpled paper ball, and the pink arrow represents the velocity of the crumpled paper ball. As you can see in my code, for Fnet on line 75, I calculated it to be this second long term being force of drag, and between lines 101 and 107, I plotted the various vector arrows. This is my final graph for my experiment. As you can see, the positions in tracker line ends at the highest vertical position, followed by the positions without drag in GlowScript, and then the positions with drag in GlowScript. I discovered in this experiment that position and time have a quadratic relationship during projectile motion, and that the derivative of this graph is acceleration, and specifically acceleration due to gravity. With the GlowScript script, force of drag plays into this, but in real life the force of drag is not as noticeable. Drag force also reduces acceleration and therefore velocity. Falling time does not rely on an object's mass. I computed this using energy, and thus mass cancels, and then if I compute this using kinematics equations, mass is never invoked. And finally, only acceleration is important to falling time within the force due to gravity.